as the name suggests, sandboxes of time, we'll be talking about sandboxing, which is well through containers. But how do we reach there? For that, we have an agenda. We'll talk about C groups. We're not doing a deep dive specifically in C groups or specifically in namespaces. It's just a segue for us to reach containers. And how do we build containers? We'll be building a container from scratch, totally from scratch, zero external libraries. We won't use run C library or containerd or any other library at all. It will be 100% completed from scratch. You can do the same thing. It's not even that hard. But for that, we'll need to understand a little bit of fundamentals. So let's start with C groups first. C groups, or otherwise known as control groups, it's a Linux feature that allows you to allocate and manage system resources. Each control group or each C group belongs to a parent group. Also used, and it's also used by container programs like Docker. Now we have C groups V1 and V2. There are two types of C groups. The legacy C group is version 1 and the newer one is version 2. There's a very good chance that your Linux operating system, be it Fedora, Ubuntu, Debian, or Arch, whatever you're using, there's a very good chance that you're using V2 if you have installed it recently in past maybe 5 years or so. Then there's a very good chance by default you're using V2. However, if you're using V1, then that's also okay. I mean, today's demo is more related to V2, but if you have V1, then we can discuss that later. It's just that I was hoping to cater to a larger audience where I'm assuming most people have V2 installed. But it's okay. If you're following along with me, um, and you can tell me whether the commands are working for you or not, and then later we can discuss the same. Okay. What are differences between C groups V1 and V2? Now, major differences. V2 follows multiple hierarchy structure, while V2 follows a single unified hierarchy. What are these hierarchies? Now, as I mentioned before, C groups follow a structure where they have a parent group and then they have child group and all. So it's a hierarchical structure. Now, in V1, hierarchy is done per resource controller. In V2, it's single and unified in a single hierarchy. How does it not look like? This is how C group V version 1 looks like. You have a root, then CPU has its own hierarchy, RAM has its own hierarchy. Same for input output devices and all. So this is how C group version 1 was. In case of C group V2, you have just one hierarchy, and then the group 1 and group 2, you can have multiple C groups there. And this is a little bit of theory. And C groups V2 are by default, as I've already mentioned. But let's see some demo. Right. Very basic, very simple demo. I already have a virtual machine set up with me. Effectively, C groups are used to limit the number of resources that a specific process can use. Docker uses the same thing. So when you go to Docker desktop and you are controlling how much memory or how much CPU a specific process can use, or rather a specific container can use, that is enforced by C groups, and C groups are a Linux kernel feature. So let's do a small demo, and I can go to, so I'll have to go to sysfsc group, this folder. If you're following along with me, so you can start with this, start with this, change directory into sysfs and C group, this specific folder. Okay, we're here. So as you can see, there are some default C groups already set up. However, we're going to create our own. So let's see, we'll create a new folder. We call it demo, and you need root permissions for this. Okay, as you can see in demo, you already have a certain number of files here. This is going to happen. These are all going to help you create C groups. These are important files. These will be created every time you create a directory within C groups. So uh, effectively, an empty or a default C group is populated for you whenever you create a folder within the C group directory, right here, within C group. So when you create a directory here, a sort of a default C group or some empty C group is created for you. You can customize this. So I'm going to make certain changes. I want to control how much memory this program is going to use. So let's say maybe let's go for echo 5. This much is enough, maybe. Let's see how this goes. This is in bytes, by the way. Maybe we'll see some program fail. This much should be enough. And I'll print it out and send the data to memory.max. So then demo slash memory, and this much This is the max memory that I'm going to allocate. Now I'm going to start a process within this C group. So it says dollar dollar. This just means the process ID of the current of the current shell that is running. Since I'm using fish, I'm going to use a slightly different command here, and I'm going to start this. So this process is already running. I'm just setting the process ID inside of this specific C group. Okay, it's done, and we can see uh, how many processes are running, or we can also check the current memory use. Hmm. It looks like we're not using any memory at all. This is interesting. Hmm. Also, let's see how many processes are currently running zero procs. I know it says my demo here. That's a typo that I made. I got confused between my demo and demo, which naming convention you use, and I accidentally mixed both of them. Hmm. This is interesting. No process is running there, it seems. I think the reason is because there simply wasn't enough memory when we set that, okay, set max memory to this much. Maybe what if we increase this total memory that we're allowed, and then set the process ID? Let's see if that works. Hmm. Interesting. Let me use this exact command here. Also, since I'm here, let me fix this and this. Hmm. Oh, I see. I ran an incorrect command earlier. I set my process ID to to some other C group instead of my own C group. Okay, current slide. Yeah, here, and hopefully things will work now. And okay, that is max, of course. Um, Wrong. Okay, this is the amount of memory we are currently consuming. Hmm. And how many processes are running? These many processes are currently running within this specific C group. Makes sense. Now, what if we change the max memory that we're allowed to use? Let's play with it a little bit. This is a virtual machine, so it's okay. I don't have a problem even if it crashes. So let's say if we set it to how much is it 618496? How many digits is it? One, two, three, four, five. Okay, one, two, three, four, five, and just a little bit. Hmm. Oh, not current max. Oh, process, echo, etc., etc. Kill. It was forced to kill, forced to die. Um, Max is set to that much. Let's set three. No problems. But let's see how are things. We still have these processes running for some reason, but they're dying. So because of lack of memory. But let's see how much memory is being used. Oh, some more memory is being used for some reason. This is quite interesting. How is this? But if we give it a little bit more memory, It still kills it, and some connection was reset apparently. Let's see how much memory are we using right now. Memory use has increased. Interesting. And how many processes are running? Just two processes. Hmm. So this is effectively the demo for zeros. You can play with it, see how much memory you can set. Maybe you can start with initially also start with some less amount of memory, and then set a process ID inside of a specific C group, and then see whether it dies or not. Then we talk about namespaces. Now again, namespaces are also a Linux kernel feature. So namespaces are going to help you isolate system resources for different processes. They allow processes to have their own system, the view of their system, making essential containerization and all that. So effectively, with namespace, you're isolating the processes. And so that the process will not know what is going on outside. And we'll do a demo, so we'll be able to understand this better. And there are several namespaces out there. Some examples are process ID namespace, mount namespace, network namespace, user namespace, etc. And let's these so like process ID namespace is going to isolate at a process level. That means the new process will not know its own actual real process ID. It will think it's process ID 1 or 2 or something else, even though actual process ID is something else. What happens is that the actual process ID is mapped to a new process ID. So kernel knows its actual process ID. And however, the process itself, it does not know its own process ID because it is isolated. It is inside of a namespace. Because of the namespace, it does not know its own process ID. In case of mount namespace, you can say this is your area now. This is the place you will be. So it will not be able to see anything beyond the specific file system it is mounted inside of. So when you say go to the when you set a specific process in a specific namespace, that specific process is going to think that the entire file system is just that specific folder that it is a part of. So it won't be able to see outside. And we'll do all this. We'll have to create a complete container. But let's do a small demo for namespaces first to understand a little bit. We do a very basic, very simple namespace, and this for this namespace, we're going to do a demo where this is effectively a Unix time sharing namespace that we are creating. So here, whatever host name that we create inside of the container will not be reflected outside. So we can do any changes here inside of the namespace in that regards. Okay, that's moving outside the home for no reason. Unshare. Um, you can run bin fish. Maybe it doesn't have to be bash. It can be anything. So now this process has started in a separate namespace. Let's see what's the host name here. Host name is obviously local domain. This is a default, but you can change it. You can call it maybe host name. Let me think of something creative. Or maybe you can give me an idea. What host name do you want me to set here? Car, cow. Okay. 0 day. Holy. Acha. Holy. Like this. I didn't read that message. Okay, I think this is long enough. Okay. Shinshan. Huh. It is invalid. Are the underscores not allowed? Interesting. Maybe underscores are not allowed. It works. But how are things outside this container or this specific namespace? It's not a container yet. Uh, Here, let's see. Host name inside container is that. Host name of namespace. Host name inside of namespace is 0 day holy cow holy shinchan. Interesting, but outside it remains localhost dot local domain, obviously because it was part of a namespace. So things and changes were not reflected outside. Makes sense. And of course, you can do uname as well. I used host name. It's okay. No problem. Same. So namespaces for isolation, C groups for controlling resources. C groups are control groups. So control groups allow you to control the resources at a very fine tune level. With control groups, you can also monitor the resources being used by a process or a set of processes. So if someone wants to do some benchmarking or profiling, that let's say I'm starting a process, or maybe if you have created a software in for Linux and you want to compare the performance of your software with another software, then one of the methods is through C groups. Simply put those processes inside of a specific C group, see how much memory, CPU, and a disk and other resources they're using, and that can be one of the ways for monitoring and profiling. Again, it's just one of the ways. There are several other ways out there. It's just an option that I'm sharing with you. Okay, chroot or change root. Again, it's just a Linux command. There's a Linux command associated with it, and it's also a system call. So it is part of the Linux kernel. Every time I use the term system call, assume it is part of the Linux kernel. It helps in security and isolation at a file system level. So it is used with mount namespace or the file system namespace. It makes sure that any process running inside of chroot cannot see outside. So to give you an analogy, let's say if you if I take you to a building, and if I tell you this building is the entire universe, and I convince you, then you'll think this building is actually the entire universe. It is not. It's just that I have told you it is, but you don't know if there's anything outside or not. Or if I give you another example from some anime, like in Attack on Titan, those people on that specific island used to think that their island is the entire world, but their island was not the entire world, right? So use cases for chroot, you can create file system jails. Like I mentioned, you can put a process, send it to a specific folder, and tell the process you stay here and you cannot go outside anymore. You cannot see outside. So it's kind of like creating file system jails. You can run legacy software. So legacy software might require some legacy libraries. So you put a software inside of a folder with all the libraries that it requires, so that it does not accidentally try to look outside of that folder, try to look for default libraries or the latest libraries. So that you create a specific folder, put all the dependencies inside of it and the program, and then you run it. And now you have a jail like situation where you can run legacy software. I think this explanation might be reminding you of something, you know putting all the dependencies in a folder and then running something. This might be triggering certain connections. You might be able to make the connection between this and maybe Docker. So this is this all things will come together. We'll get there. And use more use case for chroot. You can create virtual environments through it. It's one of the methods through which you can create virtual environments. There are more use cases. These are just few examples that I remember. Also check out chroot jail. It's a pretty good tool, and later I think you will be able to identify. You'll be able to see, or maybe you should see the difference between chroot jail and containers. There is some difference, and it's quite interesting. Now, chroot is not perfect. Chroot is not very secure. Pivot is the uh, replacement for chroot. It's a direct replacement for chroot. What's the difference? Well, chroot changes the root directory. When I use chroot, I say this new directory is the root directory. However, in case of pivotroot, it's going to move the original root directory into a different location wherever you want it to be. Well, it has to be it has to be technically part of the new root. And uh, uh, in case of pivot root, we can move the new root to into any location and move the old root inside of the new root, and then we can effectively dismount or unmount the old root and remove it. So when we are unmounting and removing a file system, the process for sure will not be able to see where did the old root code. This diminishes the possibility of any exploits or any malware getting out of your uh, new root system to a very high degree. So there's a very good chance that if you're using pivot root, the process inside of it won't be able to come outside, won't be able to it won't be able to see anything outside of that specific root or the new root, whatever you have decided. Now, of course, it's not perfect solution. If there's a vulnerability within the Linux kernel, you can just exploit it and you can and take it to your advantage and then the get out of the new root that you have created, because these namespaces are enforced by Linux kernel and they're only as strong as the Linux kernel itself. So maybe you can do a custom compilation of some Linux kernel. Maybe you can use bottled rocket by AWS or something to make it more secure. But at the end of the day, your process, your namespaces are as secure as the Linux kernel. For more security, for more effective isolation, you'll need proper virtual machines, and for even more isolation, you'll need a separate physical machine on which you run another virtual machine. Instead of that, you'll run a Docker container. Let's not go there right now. Use cases for pivot root. Now you can normally switching from initial RAM disk to the real root file system. Whenever your operating system starts, Docker and other container solutions use pivot root. System recovery and rescue, they usually use pivot root, so that system recovery can happen. It's just some use cases, just some examples. Now containers. Now containers are not like virtual machines. Containers cannot boot a different operating system entirely. Now, you might be thinking, wait a minute, I have Fedora installed, but I can run a container for Ubuntu, Debian, or whatever. Yeah, yes, you can. However, while you're in Linux, you cannot create a Windows container, you cannot create a Mac OS container. Also, your containers cannot have their own Linux modules. So let's say you create a container for Ubuntu. Within that container, you cannot have a separate set of Linux kernel modules. That is not possible because kernel remains the same. Also, within containers, in case of containers, the new container does not need to have the process ID 1. It can be anything. By default, it's 1, but it can be anything. Also, you cannot. It does not need syslog-d, cron jobs, etc. Um, Anything you can do at the kernel level, anything that you can do at the system-wide level will not be possible within containers. So, which means Docker is not a true virtual machine. You might have heard several times that Docker is a lightweight virtual machine. It's not really a virtual machine. There's not much virtualization going on here. Maybe a little bit of file system level virtualization, but that's just a zip file. Effectively, a Docker image is just a zip file. So containers are C groups plus namespaces. You don't necessarily need to have C groups. You can totally create a container without C groups as well. You just need namespaces for isolation. C groups are just for controlling the amount of resources you provide to each container. So you don't necessarily need them. It's not a strict requirement. But yeah, it's like, do you need airbags in your car? I mean, it's not 100% required. I mean, car will still work, but it's still a safety thing. So a container is just a process. There's not much to it. Now, before our demo, uh, you sh- you should probably download one of the root file systems, and this is an option. This is one of the links that you can use. Let me paste it in chat. This is just one of the places from which you can download a root file system. You can also download from somewhere else as well. You can just download Docker images as well and extract root file systems out of them. Okay, I believe it is time for our final demo where we'll be creating a small container. So I'll explain my code line by line first, and then we'll run it. Okay. As you can see, I have only imported standard libraries, format, operating system, syscall, and all this. There are no third-party libraries involved, none at all. Let's see, go.mod. As you can see, zero third-party libraries. This is where all the third-party libraries are declared in Go. So what I'm trying to say is that you can do this exact same thing in any other programming language. You can use Python, Java, C Sharp, whatever you are more interested in. C, C++, whatever. Okay. So it's a very simple program. We, st- we start by running this run function. So I take some command line arguments that what function do I need to run, and then I take some options after that. So I start with run function, and it's going to create a fork of itself. How does it create a fork of itself? So first I'm going to prepend a CLI argument with all the arguments that are passed to me. So let's say if I have, let me open, yes, can you draw? So let's say if I have these many arguments, for my process, I'm just prepending one here, and I'm calling it child. That's all I'm doing here. I'm prepending to this array. That's all there is to it. After this, I execute a command. This is proc/exe. So this is going to effectively fork my current process. By forking, I mean it's going to clone the current process. Where is it? Let's see. Proc self exe here. As you can see, these are some links. So many process IDs. These are all the process. These are related to all the processes. We can go there. Proc self. Wait. PWD. Proc and self. And exe is also here, right? So here we are effectively looking at looking at looking at all the data structure, or whether, well, a process is a data structure. We're effectively looking at the current process, and if I execute this exe file here, it's going to create a clone of the current process and make it a child of my own of the current process. So let's say the current process is running, it's going to create a clone, it's going, and new process is going to become the child of the current process. We're creating a child process basically. It's going to be child cloned process, and then we're going to assign all the we're going to assign standard input, standard output to this. But that's not important. What is important is that while cloning, I'm going to create uh, new namespaces. So here I'm creating a new Unix time sharing namespace, new process ID namespace, and this new namespace, you might be thinking what it is. This is a new mount namespace. And how do I know this? I can control plus click here, and it will explain it to me that this is a new mount namespace. I did not know this. I had to actually look it up earlier, because I kept looking for new MNT namespace, but there's no such thing as new MNT namespace within Go. Things might be a little bit different for Python, but I think this is a one-to-one mapping with Linux kernel. So there's a very good chance that this code will be very similar to how you would write in Python or Java or whatever. Anyways, when I'm cloning this specific the specific process, I'm going to provide all these system calls so that the new process that we create, the new fork that we make, will run with all these system calls, and these system calls are going to make sure that the new process runs within the layers of all these namespaces. So the next process is going to be the same process, the same program effectively, and it's going to run with CLI argument child, and child will trigger this function called child. And I'll be providing some system arguments and command line arguments here. And because I've hard coded it a little bit, I have already downloaded this Ubuntu root file system. So I go to this new file system and I use chroot. Why am I using chroot and why am I not using pivot root? Well, I wasn't able. I couldn't figure out how to make pivot root work. It kept erroring out for me, and I have no idea why it didn't work. For a long time I kept thinking that it must have been my problem, as in my code was incorrect. It must have been due to me writing incorrect code. But then I also tried using this pivot root command line tool, and that was not working either. So it was a bit confusing. Maybe we can look into it later. Anyways, after changing root, I changed the directory to go to the new root, and I run this command. That's all there is to it. So to summarize, I start this process. It's going to create a fork of itself, and it's going to create another process with all these namespaces. Within these namespaces, we create this new process. It comes here, the new process starts, and it changes the root to /home/ubuntu. It thinks this is the new root, and it changes the directory to this new root, and then it starts the new process. So let's see how it looks like. Okay, we have already compiled this, or we can compile again. It's okay. We're going to need root permissions. I'm running bin bash. Okay. I want to show you that we are running this program out of this specific directory, because we're changing the root. So I'm going to make a small change. Ubuntu bin bash, and I'm going to name it cache. Permission denied. Okay, root done. I just wanted to show you that if I do something like this now, so it's in theory, this should not work because we have changed the name of the program from bash to cache. This is not working as expected, because after changing the root, this is not supposed to work, right? After changing the root, bin cache is supposed to work, even though in real life, or rather outside of the container, we have ls/bin/bash. We have it here. And do we have cache? We don't have cache. No cache, no money, only bash. But it's okay because we have cache in our container, and we're in. We have a container now. Let's see. What is, I don't know whether it mounted proc file system or not. Okay, I forgot to mount proc file system, so I won't be able to run ps. Makes sense. But let's see, hostname is different. And what is the what does the root directory show here? This is my root directory. We have apple cat, boot, lib64, etc. What about root directory here? No apple cat, it seems. Grep apple, no apple cat here. What about home? We have Ubuntu in home directory. What about here? Ls home. We have Fedora, Linux, Brew, Mu, etc. So it looks like we are inside of a container, because this is effectively a container. This is how Docker works. But I want to verify something. I want to check if I can my mount this proc file system here. And for this, I'm going to need, I think, os.mo. No, it's just called.mo. Source target file system type, no flags, and no data. Let's see if it works. Compile and run. Okay, it runs. And we're here. It thinks the process ID is 1 or 7 or 10, whatever. It doesn't know the actual process ID. But what can we see? Can we see something inside? Cos ox. Let me see if I can grab anything. Grab cache. It would appear that yes, we can see inside. So actual process ID is 6240. However, what does cache think? Cache thinks process ID is 7, or rather, this specific process. This is cache, obviously. So cache thinks process ID is 7. However, actual process ID is 6240. It is something else entirely. So we are inside of a container, and you can monitor the container from outside, but you cannot see anything from the inside. You cannot see anything outside from inside effectively. And if I do ls, if I try to go outside, I cannot do it. Unless I try to exploit chroot. So there are publicly available exploits for chroot. It's not super secure. Maybe you can also spend some time fuzzing it. You should be able to, and if you're able to find something new, maybe you'll get a new cv for exploiting chroot. But again, chroot is not the recommended way to go about it. It's better that you use pivot root. Docker also uses pivot root because again it moves the old root instead of simply changing the root, right? So again, we can check the process id. We can change host name to क्या नाम रखूँ मैं इसका Milo, because Milo used to be a nice uh, chocolate drink that I used to drink when I was young. So it was nice. So that's why I know Milo. No other reason. Outside, obviously, no effect, no difference, no change. And this was effectively the end of the demo. Code is publicly available, and we have created a small container within just maybe 50 lines of code. The imports don't really count. So within 50-60 lines of code, you have your own container. And I'll share this presentation with you. This is this code link. I'll share this in chat.